Okay, so 1.5 elementary matrices. Okay, so we're going to start off with a bunch of simple observations. So some simple observations. The first, a lemma. So lemma, you think of it as just like a theorem, but not as big as a theorem. It's generally a tool that you use to get theorems. Okay. So a theorem is like a big mathematical result. A lemma is like a technical result that you use to affect the proof of the big result. Okay. When I was learning, when I was in college, I sort of felt like if you understood the lemmas, then you were in good shape. That is, because in the lemmas you had to do all this. It's like your hands got really dirty in the lemmas. Once you made all the tools, then the theorem is like, I pull out this one tool, and I pull out the other tool, and you use the last tool, that's it, right? But how did you make those tools? Right? That was actually key. So I felt understanding lemmas was pretty important. Okay. Okay, so so here's the lemma. It says, if you have AX equals B, an m by n linear system, and M is an m by m matrix. So that's sort of like the setting. The claim is that if M is invertible, then the system AX equals B is equivalent to MAX equals MB. So in the statement of mathematical results, there's often some sort of background information, and then there's the claim. Right? So you think, this is just sort of laying the setting, putting out the setting. You have a linear system and you have some matrix. If that matrix is invertible, then this system is equivalent to that system. Okay? So this is maybe like just the background, and here's the meat of the statement. Okay? Okay. So what this is saying is that any solution here is a solution here, right? And any solution of the second system is a solution of the first system. Okay. So what do you think about that? Right. Let's say that x naught is a solution of AX equals B, right? In other words, AX naught equals B naught equals B. Why is it then a solution of MAX equals MB? Is it?
Well, then don't you just get M times the same matrix on both sides?
Yeah.
Just multiply both sides by M. Okay, so then, right, MAX naught equals MB, right? So X naught is a solution of the second system. Right? Yeah, Mia.
What is M?
M is just some matrix. So you have a system and you have some matrix. Okay, and if the matrix is invertible, then this system is equivalent to this system. Okay, so to make it concrete, you have some system, 1, 2, 3, 4 times xy, x1, x2 equals, say, 1, 0. Okay, so here's your AX. You have some system, AX equals B, and you have some matrix. You have some matrix M, let's say it's 1, 2, 2, 1. Okay. And what we're saying is that if M is invertible, and this M is invertible, then this system is equivalent to, this system is equivalent to this system, right? So if you want to work it out, right, this is so 7, 8, 10, 2, 3, 5, 4, 4, 8. Right? So what this theorem says is that the system x1 plus 2x2 equals 1, 3x1 plus 4x2 equals 0 has exactly the same solution set as this one.
Even if you don't multiply b times n.
Oh, I'm sorry, I should have. Sorry, my mistake. Sorry. 1, 2, 2, 1, 0. I should have gotten 1, 2. Thank you.
Oh, okay. Okay, that makes sense.
And so, yeah.
Does M have to be invertible just to avoid this all zeros cases?
Well, all we've shown so far is that if you're a solution of the first system, then you're a solution of the second. And you notice that we haven't used invertibility at all. Okay. So where do we use it? We need to go backwards, right? So conversely, right? If x naught is a solution of max equals mb, then why is it a solution of ax equals b? Because you multiply on the left by the inverse function, by the inverse matrix, right? Then, right? In other words, max naught equals mb. Well then, m inverse max naught equals m inverse mb, and so x naught is a solution of the first system. Okay. So, pretty simple. All we're saying is that if you're a solution of the first system, you're a solution of the second. If you're a solution of the second system, you're a solution of the first. And so these are equivalent systems, as long as the thing is invertible. Okay, and so you notice that we needed invertibility to get back again. Okay, so this first part didn't require invertibility at all. Right? It's always true that if x is the solution of this, then x is the solution of max naught plus mb naught for any matrix M. Right? Right? We needed invertibility to say that the solution sets were actually equal to each other. Okay. Okay. Is that clear? I've talked about it more than I planned. It's actually very simple, right? If you have a solution of this, right? If your x solves this, multiply on the left by m. Oh look, it solves this. The end, right? If your x solves this and your m is invertible, multiply on the left by m inverse. Then your solution of this thing. The end. Okay, that's it. So trivial statement, but maybe if we had talked about it at the beginning, it wouldn't have been so trivial. Okay. Okay. Okay, so second simple observation. So another simple observation. Okay, so let's recall the elementary row operations. So recall elementary row operations, right? they were that you could switch two rows, right? You could multiply, you could scale a row, right, by a non-zero vector. A non-zero scalar, excuse me. And you could add a multiple of one row onto another. Okay. Those were the elementary row operations. And here's the observation. So here's the observation. One can affect a row operation by applying that operation to the identity matrix and then left multiplying. By the resulting matrix. Okay, so for example, right, if I have this matrix A11, A12, A13, A21, A22, A23, A31, A32, A33, and I want to do a switch of the first and third rows on it, okay, by using a matrix. Well, what I do is I take the identity matrix and I switch the first and third rows of the identity matrix. I switch those guys. And then I left multiply by that, and you see what happens. Right? I'm going to get the third row and the first row get switched. Right? So this matrix, executed the elementary row operation that was done on the identity to get this matrix. If I wanted to multiply the first row by 5, well, I take the identity matrix and multiply the first row by 5, right? And then that would give that this matrix would do the row operation of multiplying the first row by 5, right? If I wanted to add on 5 copies of the first row onto the last row, well, I would do exactly that to the identity matrix, and this matrix would do that to whatever matrix you multiplied it, you left multiplied by. Yeah, Zane?
So what's the purpose of that operation if you could just switch the rows?
Oh, like why not just say let's switch the rows?
Yeah.
Yeah. Well, you'll see. So
Okay.
So instead of it allows us to express everything as matrices rather than as operations, and you'll see why that's handy, why that turns out to be very handy. Although this observation is pretty simple. Okay, so these matrices. Matrices so obtained, right? A matrix T obtained from I via a single elementary row operation is called an elementary matrix. So all these guys over here that I wrote down while I was talking, These are all elementary. These are all elementary matrices. Okay. Okay. One other simple observation. Every elementary matrix is invertible. Every elementary matrix is invertible. Right. Is that obvious? There's going to be some matrix that reverses the effects. Right? Well, if you have a switch matrix, right, what's its inverse going to be? Henry? Are you the one who's whispering? Who is whispering? Somebody's whispering. Kathleen, is it?
Originally switched from switching to
So here I have this switch matrix. So it's switch the first and third rows. Okay. What is going to be what matrix will undo that? Anna?
Yeah, the inverted I matrix. The I matrix in which you switch the rows around a bit, like the one you did.
So yeah, so like here I have a matrix. Here's an elementary matrix, right? It switches the first and third rows, right? I'd like to have a matrix that when I multiply this guy, I get the identity. What matrix will do that? Yeah, Mia.
Would it be the exact same matrix?
The exact same matrix, right?
Mhm.
Right? You just make the matrix that switches the first and third rows. You multiply them together, you have a matrix that does nothing, right? In other words, the identity matrix, right? So you just make an elementary matrix that undoes the operation, right? Elementary row operations are all reversible by elementary row operations, right? A switch of two rows is undone by the switching the same rows, right? Multiplying a row by a scalar is accomplished by multiplying the row by by 1 over the scalar, right? Adding 5 copies of the first row. If I added 5 copies of the first row into the third row, well then, right? If I added 5 copies of the first row onto the third row, what should be my inverse matrix? The one that adds on negative 5 copies of the first row, right? And those will, those row operations cancel each other out, and so you're going to get a matrix that does nothing. In other words, the identity. Okay, so all elementary matrices are invertible. Okay. So we're just going to make one sort of unremarkable observation after another today.
Yay.
Yeah. So I'm not sure when I'll stop apologizing to you for how boring the lectures are, but at least today it's still gonna be not that exciting. Yeah, Henry.
You mentioned something about a switch matrix?
Yeah. I just made a matrix that switches the rows.
Okay.
A matrix that came from the row operation of switching 2 rows. Okay? Okay. So another non-interesting statement. We say the matrix A is row equivalent. Maybe if I go quickly, it'll seem like it's interesting. To B, if A can be obtained from B via elementary row operations. Right? In other words, you can hit A with a bunch of elementary matrices and end up with B. Right? That is, and we'll write this. A is equivalent to B. That is, there exist elementary matrices E1, E2, En, such that B is A hit with E1, E2 up to En. So being row equivalent means that you can take one matrix and hit it with do a bunch of elementary row operations and end up with the other matrix. That's something we've done before, right? That was the Gaussian reduction, right? We tried what we tried to do was take one matrix and then find out if it was row equivalent to a triangular matrix. Right? That was Gaussian elimination. Okay. Sort of easy question. If A is row equivalent to B, is B row equivalent to A? If A can be obtained from B via elementary row operations, can B be obtained from A via elementary row operations? I mean, go ahead.
Yeah, because the elementary matrices are invertible.
Yeah, exactly. Right. So you just invert everybody and move them all to the one by one, or en masse, you move them to the other side. Right. So sure. Right. En inverse, En minus 1 inverse, E1 inverse, B is A. Right. If A is equivalent to B and B to C, is A equivalent to C? Sure, right, obvious. Okay, and such a relation is called, just as a remark, such a relation is called an equivalence relation. I guess there's actually one more thing you need to add, that something is equivalent to itself. But if you satisfy these three, transitivity, symmetry, and being equivalent to yourself, then you're called an equivalence relation. So this row equivalence is an equivalence relation, is how we express this thing right here. Okay. Okay. So now we can get something which we'll call a characterization of invertibility. So here we go. Here's the theorem. Let A be a square matrix. Then the following are equivalent. So you'll see this often, this sort of notation often. The following are equivalent. Following are equivalent. And they're logically equivalent. Each one of them implies the other. Each one of them is equivalent to the other. Okay? So A is invertible to AX equals 0 as a unique solution, namely the zero vector. 3, A is row equivalent to the identity matrix, and 4, A is a product of elementary matrices. Okay, so this theorem will give us a way of describing or recognizing when a matrix is invertible.
Sorry.
Okay, so A is invertible is equivalent to the system having a unique solution, is equivalent to A being row equivalent to the identity matrix, is equivalent to A being a product of elementary matrices. Okay, and so here, maybe you see the significance of those matrices. You know, why do we care about those matrices at all? In fact, all invertible matrices are simply products of elementary matrices. Okay. All invertible matrices, they all can be broken down into products of elementary matrices. And you start off with elementary matrices and you multiply them together, then you end up with all invertible matrices, conversely. Okay. So again, this TFAE means that each of these statements is equivalent to the other. And so to prove them, you might think you have to prove this implies this implies that. 1 implies 2, 2 implies 1, and 1, 2 implies 3, 3 implies 2, whatever, right? Usually what one does is prove that 1 implies 2, 2 implies 3, 3 implies 4. You set them up in a ring, and 4 implies 1, right? Because then proving that set of implications shows that they are all logically equivalent to each other. Okay? And that's what we'll do now. Okay. Proof 1 implies 2. If you're invertible, then AX equals 0 has a unique solution. If A is invertible, then AX equals 0 has a unique solution. Let's do number 2. Right? Because that's obvious, right? Right? If A is invertible, then AX equals 0 has a unique solution. Right? If A is invertible, then if AX equals 0, you see that X equals 0. So you have a unique solution. Right? So it's trivial. So obvious. Right? X equals 0, so you have a solution, X equals 0, and it's the only solution. Right? There's nothing else that could happen. Okay. 2 implies 3. This one is a little bit trickier. So if AX equals 0 has a unique solution, then why is it true that A must be row equivalent to the identity matrix? Okay, this one's a little bit trickier. You say, okay, reduce A to reduce row echelon form. Okay, reduce A to reduce row echelon form. Okay, and suppose alpha II equals 0. Right? Suppose that one of the diagonal entries is 0. Okay, like maybe the first one is 0. Okay. Suppose one of the diagonal entries in the reduced row echelon form is 0. Right? Well, that would mean that the last row is all zeros. That would mean that the last row is all zeros, right? Because it's a square matrix. Say it's n by n, right? Then you start off with 1 here, right? There's no way you're going to have ones all the way down. You can't have ones. It's sort of hard to explain, but you can't have ones all the way down the diagonal. The best you could end up with is a 1 here, maybe, right? Anyway, the last row is doomed to be all zeros then, right? If any of these guys, if any of the diagonals is not 1, then the last row is going to be all zeros. Okay. If you think about how the reduced form looks. Okay. But if that last row is all zeros, well then, and this homogeneous system that has not only one solution, it'll have infinitely many solutions, right? Because you're going to have free variables then. right, has infinitely many solutions. Right, because of the existence, because has free variables. Right. Right. And so the reduced row echelon form of A must have ones down the diagonal. In other words, it must be the identity. Must be the identity matrix. Right, so, right, we, let me phrase it as a contradiction. This thing has infinitely many solutions, contradiction, right? We assumed it had only one solution, right? And thus, none of the diagonal elements could be 0, and so the reduced row echelon form must be the identity. Okay, just to phrase it more clearly. Does that make sense? That's probably the hardest step among these implications. Does that make sense? Right? Why is it true that if you have a unique solution that you're equivalent to the identity matrix? Well, suppose you have a unique solution and do the Gauss-Jordan reduction. If one of the elements in your Gauss-Jordan form, in your reduced row echelon form is 0, then you have infinitely many solutions. Contradiction. So your reduced row echelon form must be the identity. In other words, Gauss-Jordan gets you to the identity, right? So Gauss-Jordan gets you to the identity. So you are equivalent, you are row equivalent to the identity. Okay. Any questions about that? Any questions? Okay. If it's confusing, go and think about it. That's okay. Yeah. Certainly, I'd say I understood probably like only 5% of whatever was said in class, and then I went home and thought about it, right, in college. So if you understand nothing, you're not far off from where I was. Right? But just go home and think about it, right? And that will be the difference, right? If you don't go home and think about it, then you'll be very different from where I was. Right? But understanding nothing in class to me is almost like how it ought to be. That is, it's no great chat. It doesn't appear to me to be a tragedy if you're confused. But if you're understanding, even better. Okay. So 3 implies 4. Okay. 3 implies 4. If A is equivalent to is row equivalent to the identity matrix, then it's a product of elementary matrices.
Yeah.
Right.
How is
Yeah.
that's
Is
not
that
any different
obvious?
from just
That's almost the same
isn't
statement.
it the
Yeah,
definition?
That's the same statement, right? So to be equivalent to the identity matrix means that you can get to A from the identity matrix via elementary matrices. In other words, A is a product of elementary matrices. Right? So, tautology. Number 4 implies number 1. If you're a product of elementary matrices, then you're invertible. Why is that? Why is that obvious? If you're a product of elementary matrices, then you are invertible.
Perform the opposite, like what we just did.
Yeah.
Okay, certainly. You could say, just invert each one of these guys in the opposite order, right? So just multiply on the left by En inverse, En minus 1 inverse, blah, blah, blah. Or you could say, a product of invertible matrices is invertible. Right? That's something that we observed earlier. Right? If you have these guys and they are inverses, they are invertible, then their inverse exists. Right? The product of if A and B are invertible, then AB is invertible. A product of elementary matrices is invertible. A product of invertible matrices, excuse me, is invertible. Right? En through E1 inverse is E1 inverse through En inverse. And so we've completed the ring, right? So we've completed this ring. Okay, so all these things are equivalent. This is a characterization of what it means to be an invertible matrix. So now we know every invertible matrix is a product of elementary matrices, can be reduced to the identity matrix. This is maybe the useful one. Can be reduced to the identity matrix. I should say that there's another one. AX equals B as a unique solution for each B. There's actually another condition that's equivalent to all these guys, but we'll, I don't know if we'll prove it. I think I may just state it. Okay. Okay. So this leads us to another dull thing. The computation of inverses, which is an exercise in, I'm sorry to say, bookkeeping. So, bookkeeping. Right, so we just observed that A is invertible, then A is equivalent to the identity matrix. That is to say that there exist elementary matrices such that En through E1 times A is the identity matrix, right? So if you can do this, if you start with your A and you apply a bunch of elementary matrices to it and you get the identity matrix, you have found your inverse. This is it. This is it right here, right? If you start with A, right? Well then, in that case, A inverse is exactly this En through E1. Right? So that suggests a way of calculating the inverse. So here is the method. If you would sort of honor it with that title, it's not really that great. One starts with the matrix on one side and the identity on the other, and then change A, or try to change A into the identity matrix by applying elementary matrices. Okay. At the same time, apply them to both sides. To apply them also to I, to the I on the right-hand side, to keep track. So you start off with your A, and you hit it with some row operation. You keep track of that. You do the same operation to the right-hand side. You do another operation. You do that operation to the right-hand side. You keep on going until you get as close to the identity as possible, right? Okay. So you start from here, and you just keep on applying row operation after the next, doing basically Gauss-Jordan reduction. Okay. If at the end one has the identity on the left, then the right-hand side is the inverse, right? Because if this thing is the identity, that means that En through E1 was the inverse. And luckily for you, you've kept track of what it is on the right-hand side. Okay. So it's not, you know, it's not particularly exciting, but this is how one does it, right? So if I have some matrix 1, 3, -2, 2, 5, -3, -3, 2, 4, -3, 2, -4, and I want to figure out its inverse matrix, well, you know, I just take this guy and I start applying elementary row operations to it to get it to reduce row echelon form. So the first thing I'm going to do is, you know, take -2 of the first and add it onto the second, right? So -2 of the first, add it onto the second. Right, so I get this minus twice. So this one stays the same, 0. This minus twice that is -1. This minus twice that is 1. -3, 2, 4. Right. Then I'm going to take, say, 3 of the first and add it onto the last. 1, 3, -2, 1, 0, 0. -2, 1, 0. 3, 0, 1. 0, -1, 1. 0, 3 of this guy, add it onto that, 11, 3 of that guy, -6, -10. Right? And I keep on going. I'm gonna multiply this guy. I'm sorry. I'm gonna add on 11 of this guy onto that guy. Right? Add on 11 of this guy on so. Right, so I get 0, 0, 11 of that guy, I get 1, 11 of that guy, I get -19, 11, 1. Right, and multiply this guy by, well, that is obviously there. Right, and you keep on going, I'm not going to do it, maybe. It's not that exciting. You keep on going until you, should we finish it? Should we finish it, or is it clear what we need to do? What we need to do, of course, is just keep on going until we get the identity matrix on. You see that at this point, we can get the identity matrix. Right? Keep on going until you do, and then when you do, whatever you have on the right-hand side, that will be your inverse matrix. Okay? So that's that. It's yeah. Okay. So the most important thing, I think, is in this lecture is the characterization of invertibility. Okay. Okay, that's it for today. Next time we'll go into chapter 2, the determinant. That will start to get more interesting.
Thank you.
Okay, see you.
Thank you.
Yeah. Thank you. Enjoy your weekend.
Thank you, Teresa.
I think that's upstairs.
See you.
Was it better when